Today's theme is related to a model of yarn hyannis. You know principally that on the yarn surface is something which we call as a hyannis sphere. It is the sphere in which our fibers have very probabilistic character of their shapes. Therefore, also the model of this sphere must be a stochastic model. It will be maybe a little difficult for you, but I want to speak slowly, and please concentrate your mind to logical operations, a logical sense of the steps which we will together to do. In hyannis sphere, between some two radii R1 and R2 are different shapes of fibers. It's symbolically something in a cross section. There are fibers type 1, for example, as here, some free ends. Then a fiber type 2, like some loop. Also, the fibers type 3, some protruding segments, fiber segments, type 3. There are existing also fibers type 4 and 5 here. Fibers type 4 are reversal ends, and fibers type 5 are reversal loop. We can assume that the number of such shapes, reversal ends and reversal loops, are not too high, and therefore we neglect this, I can say, atypical fiber shapes. So we have only fiber shapes number 1, 2, and 3. The loop type 2, we can hypothetically, of course, no really, we have not knife for such fibers in the moment. Only hypothetically we can divide based on such a red line, so that we obtain from one loop two ends, to A and to B. Yeah? So then we will solve the structure in hyannis sphere where free ends and protruding segments are only. This is the scheme of some yarn and its hyannis sphere. Radius of yarn body is our known yarn diameter d, this here. Yeah? We will often use also 1/2 of this, so yarn radius rd. All quantities which are related to this radius rd will have subscript capital D on the yarn body surface on the diameter d. Yeah? Well, r, some higher radius r, is a general radius, evidently higher than rd. Rd is the smallest radius for hyannis sphere. And fibers are going to the maximum of radius r max, which is radius of end of longest fiber segment. So that in the hyannis sphere, in reality the radius is going from rd through general r to the r max. Yeah? A number of protruding fibers. At the radius rd, it is surface of a yarn body, compact part of yarn body. On this, the number of protruding fibers is md. I can say number of our red points is MD. Is it shown? Okay. On the general radius R, number of protruding fibers is called as M, and this quantity M based on radius R. Intuitively we can say that with increasing of radius, the number of protruding fibers are decreased, isn't it? Number of our green points in our scheme. Acceptable, understandable. Well, in the differential layer, on the radius RD, on the yarn surface, is some value of packing density. This packing density we call mu d. This is a packing density on this, in vicinity on this cylinder surface having radius RD. Yeah? In a general radius R, the corresponding fiber packing density is mu. You can imagine that this mu is smaller than mu d, because some fibers have end between this radius RD and R. So, packing density mu R is also some function of radius, decreasing function of radius, isn't it? Yes. Terminologically, I will speak about the fibers, but in each case I mean the segment of fibers which is lying in hyannis sphere. So under the term fiber in this lecture, please understand the fiber hair in hyannis sphere. Yeah. Okay. What about number of protruding fibers? It is M at the radius R, isn't it? And generally say M plus dm at the radius R plus dr. Because number is with radius decreasing, this dm must be negative. So minus dm, this elemental increasing is dm, and this is negative. So minus dm, it is higher than 0, isn't it? Well, the probability that the end of fiber which is passing through radius R lies within the differential layer between R and R plus dr. Differential layer is known imagination. We know it from helical model, first time, isn't it? And so on. So the probability that the end of fiber which is passing through radius R lies within the differential layer R from R to R plus dr is some elemental quantity phi r dr, where the positive function phi r is a suitable function of radius R. What it means, it's shown on this picture. Let's imagine a fiber which is protruding some general radius R, this black fiber. Yeah? How is the probability that its end will be immediately after it's protruding through radius R in a differential layer from R to R plus dr? Schematically, how is the probability that this end of this fiber is lying in this yellow, this red point, yeah? End point is lying in this yellow differential layer. How is the probability? It's differentially small probability, isn't it? So it is something which is related to dr, and we can call this probability as phi r dr, where phi r is some real function and dr is differential small quantity of radius. Okay? So probability that the this fiber have its end immediately after protruding the radius r is phi r dr. The number of fiber ends in the differential layer, in such differential layer, is minus dm, because to have the positive quantity, yeah? Minus dm. And what is it? Whole total number of protruding fibers on radius r we called m. So m times probability. Now all fibers have their end in our differential layer. A lot of fibers are having end in some higher radius. So total number m times probability, phi r dr. From this equation it's possible to rearrange to such form and integrate it from on left hand side from over m, from md to m, from starting position on the radius rd to the general position on the radius r, and right hand side from rd to r, because don't have the same symbol for integrating variable and upper limit of our integrals. We use an other alphabets, but it is only integrating name of integrating variable. Yeah? So on the place of r here I use w, because sorry, on the place of m I use w, because m is now the upper limit of our integral, and the same is here. After integration of this both sides, we obtain then logarithm m minus logarithm md is minus integral from rd to r of the function phi t dt, or m by md is e power 2. You know that we often use graphically if the exponent is too especially large and complicated, we don't write e and exponent, we usually write exp, and in brackets is this value of exponent. So I hope you know this convention. So m by md is e power 2 minus this integral, or the number of protruding fibers m on general radius r is md, starting number of fibers, our earlier red points, times e power 2 minus this, minus such integral. The total number of fiber ends in the hyannis sphere is md. Now evidently, each fibers which starting in yarn body surface must also end it in our space. Yeah? So the total number of fiber ends in whole hyannis sphere is md. The number of fiber ends in the interval from r minus rd, it means from the minimum radius rd to our general radius r. How many fiber ends is in this layer from rd to r? It must be md minus m. md is the maximum value on the radius rd. M is the number of protruding fibers on the radius r. The differences must be the fibers which are finished earlier than is coming the general radius r. Well, let's call psi r as a ratio md minus m, number of fiber ends in interval from rd to r, by total number of all fiber ends in hyannis sphere. So it is 1 minus m by md. using, for this ratio, earlier derived equation, we obtain psi r is 1 minus e power 2 minus this integral. Well, when you will think about the sense of this function capital psi, you must say that psi is also the distribution function of a number of fiber ends. Intuitively, on the radius RD, the value is 0. Yeah? Because from RD to RD is 0 fiber ends. On R max, in maximum possible radius, this value is 1, because all fibers had its ends before the maximum radius R max. Yeah? Well, so psi has the sense of the function psi is the distribution function of number of fiber ends. How it is on the radius R formally when we write it? It is, if R is RD, the minimum radius, I must on the place of R write RD, so that I obtain this here. But integral from RD to RD is equal 0, evidently. Yeah? So that it is this 1 minus 1 is 0. Okay? Well, it corresponds to our intuitive feeling. This function is equal 0 for R equal RD. For R equal R max, it must be equal 1. From point of view of logic as well as formally, we know what is it, the distribution function. It must be equal 1. And so, it must be valid, that is 1. 1 is, now it is 1, 1 is 1 minus e power to this integral. This integral is from RD to R max. So that 1 is on the left hand side, 1 is on the right hand side. We can write 0, because 1 minus 1, yeah, is equal 0. 0 is minus 1 by e power to this integral. And what is going out? That this integral must limit it to infinity, because this ratio be 0. We will need it later. Well, generals say we must prepare set of general equations. It will be our first part of our activity. Then we will introduce some assumptions, and we will more precise our general equations. Now we are in the first part of our activity. We formulate the general equations. Let's imagine one elemental part, one element of fiber in hyannis sphere, which is on the radius R and is protruding some elemental layer, thickness dr. Yeah? Imaginable. Okay. This is some fiber element, length dl. We can speak about the local Cartesian coordinates, x, which is radial, y, which is tangential, and z, which is axial direction to our, in relation to our fiber element. Well, this fiber element have 3 angles to our local axis. To the axis S, to the axis X, it is the angle theta r. To the axis Y, it is the angle theta t, tangential direction. And to the axis Z, to the axial direction, it is angle tangent A. Well, length of the fiber, of this fiber element, is dr by cosinus theta r, as it is evident from this scheme. M was number of fiber elements inside the differential layer. Inside this differential layer. These elements, we can have some numbers 1, 2, 3, 4, generally subscript I, which is 1, 2, and so on to the last number m, because m fiber elements is protruding our layer. It will be index subscript. How is the mean length of fiber element? Now we must sum all fiber elements from first to the last, from 1 to m, and divide by m as each mean value. So this is mean length of fiber element. We can also write it in this form. Why not? Because dl is this here. And also it's possible to write it formally in the expression dr times lambda r, where lambda r is this expression. This is the same. What is a sense of lambda r? It's a mean value of all reciproc values of cosinus theta from all fibers in our differential layer. Well, and it needn't be same in each radius. Therefore, generally, this lambda is a function of radius. In another radius, such value is another quantity. Well, let's similarly define also another function, sigma r. It is similar than earlier postulate equation, but here is the angle theta a. So it is arithmetical mean from all reciproc values of angles theta a over all fibers in our differential layer. The total length of all fiber elements in our layer. What is it? D capital L. Yeah? No, it is sum of all portions which are elemental portions which are lying in our differential layer. Is it all imaginable? So it is also number of such protruding elements times mean length per one element, isn't it? And this is based on earlier equation. M is this here, and this is lambda r dr. Yeah? So, if the length of yarn segment is called zeta, it means, let's imagine we analyze some yarn portion, yarn segment, length theta. The length of our yarn is zeta. Zeta. The volume of differential layer, what is the volume of differential layer? Our known differential annulus times length. Differential annulus have the area 2 pi r dr times L. Zeta. Length of yarn is zeta. So 2 pi r dr times length of the yarn, zeta. This is the volume of differential layer, whole volume, total volume of this differential layer. The fiber volume inside this layer is total length of fiber elements which are protruding our differential layer, D capital L. We derived it, yeah, times fiber cross section, S. So dV is S times dl. And using known definition, what is it? Fiber packing density. It is every times fiber volume by total volume. There now it is fiber volume in our differential layer by total volume in our differential layer. So we obtain SL by 2 pi r dr zeta. On the place of dl we use this equation, and then after rearranging, we obtain this expression for packing density in hyannis sphere on general radius r. Yeah? The packing density of fibers on the radius r equal rd is the starting packing density mu d. Starting, I mean, on the surface or yarn body. How is this packing density? No, on the place of r, here, here, and here, we need to give a quantity rd. It's here. This is 0, so that we obtain mu d is equal to this expression. Or we can write from mu d is equal to this, also that mu d times rd by lambda rd is S times md by 2 pi z. It's only rearranged. The ratio mu d times rd by lambda rd, mu d rd by lambda rd, let's call as some parameter c dash. Yeah? It is not function of radius. It is some parameter of this hyannis sphere, of this yarn. Then the packing density can be expressed as shown, can be expressed through this equation. No more. Well, good. The mean sectional area of ith fiber. Ith fiber, general fiber, have some green sectional area S star, which is no first time in set of our lecture, we know it, which is cross-sectional area of fiber S by cosinus of corresponding angle. In this case, it is an angle theta A. Is it? Yeah? Yeah. This is the theta A. Yeah? Okay, we are right. So it is cosinus theta A. Mean sectional area of fibers at radius r is which? We must make the mean value or average value, which is sum of all sectional, this green sectional areas by number. How many are there? M. So that it is this here. We can write it because S star is S, so we obtain this here. And because we earlier postulate the function sigma r, we can write it also in the form S times sigma r. Well, how is the fiber number of fibers in whole hyannis region? The cross-sectional area of fibers lying in the differential layer, we have here some differential layer in a cross-section. Yeah? ds, what was ds? You know it from helical model, for example. Total area 2 pi r dr times packing density times mu. So is this is the red area in some general differential layer. Yeah? This red area here. Number of fibers in such layer is ds by S star bar, mean value of mean sectional area of fiber on the radius r, isn't it? Yeah? Similar logic was in helical model when we derived number of fibers in the yarn based on idea of ideal helical model. Similar logic. So the number of fibers in this layer is dnh, which is fiber area, this red area ds by a star bar, mean value per one fiber section. So dn is, using equation derived earlier, d and h is given by such expression. I use only on the place of a star bar. This here, and on the place of ds, where it is? Oh, yeah. ds is here, 2 pi r dr mu, yeah? Okay. How is the number of fibers in the whole hyannis region in yarn cross-section? In one differential layer in cross-section, we see D and H fibers. But the axial points of our fibers. How is the total number of fibers in yarn cross-section in the sphere of hyannis? No, it is sum. It's sum, isn't it? Sum of all these numbers over all differential layers, starting on the radius RD to the maximum possible radius, which is R max. It's clear, I think. I said to you earlier how was the history of symbol of integral. So from that time you know that Wilhelm Leibniz, very known mathematician, knew that give together, sum together, infinity number of infinity small parts is some special type of summation. So therefore, because Latin summation is summa, he used symbol S, capital S, as a symbol of such type of summation. And because there was some mistakes with alphabet S and this operator S, then he made this S longer to today's integral. You know this history. So what is it, how we must to sum the number of fibers over all differential layers? Using integration. We must make integral from D and H, from R equal RD to R max, using equation derived earlier, this here, we obtain an H in such expression. Yes. And we have maybe all necessary equations for solving of our problem. But what's the problem based on practical side of our model? In our model, we have 3 unknown functions. One is the function phi r, which is related to the probability of fiber end on radius r. And then the couple of functions, sigma r, and the second was, how was it? One moment. Sigma r and lambda r, yeah. Lambda r, this is the function of radius. Then sigma r, this is also the function of radius. And then phi r. These 3 functions we don't know. So, let's accept some assumptions for simplification of whole our problem. Assumption 1. Let's assume that the probability that the fiber passing through radius r has its end lying in the differential layer for r to r plus dr doesn't depend on radius. In each radius, if the fiber is protruding this radius, the fiber have same chance to be finished, independently to value of radius. Okay? Do you imagine this assumption? Yes. So, then the probability, our probability, is independent to radius. Then the general, say, function phi is based on this assumption constant. The function phi r is a constant phi, common constant for each radii. We derived that integral for id from rd to r max phi t dt must be equal infinity, or must limit it to infinity. Be more precise in formulation. Okay. Now what is it? Integral of constant phi dt is phi times r max minus rd, and it shall be equal infinity. It must be equal infinity. Phi, because it defines some probability, and the fibers must finish. Phi must be some real quantity higher than 0. Then r max minus rd must be infinity. Rd is not is given value, so that r max must be equal infinity. In such model, when we accept this assumption, the hyannis sphere, we have a smaller number of protruding fibers, but it is going to the infinity. The maximum radius is going to the infinity. It's not real, but no too difficult, because the Longis fibers are only a few, and then we will, in each case, dominant part of air in long distance from yarn body. So it is possible to accept. Assumption 2. The random orientation of fiber is independent of radius. Our fibers, or fiber segments, theoretically infinitesimally small fiber portions, in disordered radius, have very difficult directions. Difficult to formulate some probability density function of orientation of fibers in a sphere of hyannis. Each fiber have another direction. It exists some distribution of such directions. And we here assume that the distribution of fiber directions is same in each radius. In small radius, I speak about the hyannis sphere only. In small radius, relatively small radius, exists some distribution of directions. On higher value of radius, the distribution of directions have the same character, is same. Yeah? This is logical sense of our assumption 2. If it is so, then the quantities lambda r, the functions lambda r and sigma r are not functions, they are constants. So that this is lambda, it's constant, and this is also sigma is constant. Yeah? It is our second assumption. Is understandable? The logic lies in then that the distribution of fiber orientation is independent to radii. Now let's, based on such assumptions, or this couple of assumptions, let's rearrange our earlier general equations to new form. Number of protruding fibers, m. We derived m is this expression here. Now phi is constant. So it is going before and after integrating, which is trivial, we obtain that m is md times e power to minus phi r minus rd. Well. On some general radius r, and number of protruding fibers is m. In in another higher radius, number of protruding fibers is only 1/2 of earlier quantity m. Yeah, on radius r, number of protruding fibers is m. In another radius, higher radius, number of protruding fibers is 1/2 of this earlier quantity m. Yeah? This longer, higher radius is some radius r plus h. So h is some distance in the radius. So on radius r is m protruding fibers. On the radius r plus dh, some higher, I don't know in the moment what is the h, number of protruding fibers is m by 2, okay? So it is valid. This equation is valid. And now on the radius r plus h, the number of protruding fibers is m by 2 on left hand side. And it is based on this general equation here. It is md times e, but on the place of r, I must give r plus h, yeah? New radius, higher value of radius. Well, after rearranging, I obtain this here. But this part, it is earlier m. So I have the equation m by 2 is m times e power 2 something, minus phi h. So we obtain 1/2 is e power 2 minus phi h. After rearranging, we obtain that h is logarithm 2 by phi. And because phi is constant, h is also constant, yeah? Independent to radius. Or we will use also that the phi is logarithm 2 by h. So what is the sense of h? Every time when I increase radius value plus h, radius plus h, I obtain a new bigger cylinder where number of protruding fibers is 1/2. Therefore, we can call this quantity h as a half decrease interval of number of protruding fibers. Every time when I jump from some radius r to the value r plus h, number of protruding fibers decrease to 1/2. Similar situation is in nuclear physics. You know the half time or how it is in the English. Yeah. Half decrease interval. Using on the place of phi logarithm 2 by h, after small rearranging, we obtain that the number of protruding fibers is starting number and d times 2 power 2 r minus d by h. Well, how it is now with packing density? For packing density, we derived in general part of our derivation this formula, this equation. Now this is constant 2. We can use it, rearrange, use on the place of phi, use this here, and we obtain this expression. Where c dash was this here. Now because lambda is constant, it is mu drd by lambda. We can also introduce, I can say, final constant c, which is mu drd 2 power 2 rd by h, rd, so that it is also not the function of radius. And then the packing density, this mu, which is given by this formula, because this is c, we obtain the formula mu is c by r, 2 minus r by h. Of course, when we want to calculate the packing density on given radius r, we need to know two quantities. The characteristic h half decrease interval value, and the characteristic constant C. Yeah? Number of fibers in the differential layer. Number of fibers in the differential layer, DNH, it was this here. We derived it on an earlier slide. Sigma r is now constant sigma, so that it is this here. And on the place of mu here, we use this expression so that we obtain this here. And then those DNH is equal to this expression. Well, total number of whole fibers in yarn cross section, but only in the sphere of hyannis. Only in the sphere of hyannis is NH, which is integral from r equal rd to now infinity, because r max is now infinity. From DNH, using it after small rearranging, we obtain such expression, and finally this expression. The derivation which I jump are very trivial. It's only rearranging, or as in this case, e power to something integrate. Not this is a toy for you. Okay. We can measure, one method how we can measure hyannis of the yarn is that we use some parallel fiber beams, some light, and we make some projection of the yarn. What we see on the microscope, for example. In the central part, we see a black, we will later show it more precisely, only intuitively. In the central part, we see a black points. Then we see some light windows among the black curves of fiber. The light windows are larger and larger with radius, and then only light, isn't it? This is the typical picture of the yarn. One moment. One picture. Like this here. Yeah? From this, this is easy to obtain. It is easy to obtain this picture and evaluate this picture using, for example, image analysis technique and similar tools which you know from laboratory. Therefore, we want to derive how is the possibility of light beams go beside the yarn. So that let's imagine a set of light beams, orange light beams in our picture, which are going beside our yarn on the distance x. Can you imagine it, yeah? There are light beams. Some of them, this light beam, this light beam, this light beam, this, can go beside the yarn without problems. Another, for example, this light beam, this here, are hindered through fibers, through hairs, which are on the yarn surface, isn't it? Symbolically, there are these light blue points in our picture. The fiber arrangement is random, of course. Yes, in this picture is one mistake. It shall be here in reality 2 rings, because this is, it's my mistake. I proved yesterday to repair it, but because this picture is from older software and I have a newer software, it brings me no good results. It's typical, the relation between theory and praxis. The companies which produced software said it's perfect compatible. But when we have a more sophisticated problem, you can see that perfect is not compatible. Excuse me, nobody is perfect. And let's imagine that we have here not only one ring. It is scheme of cross-section of yarn. We have not here only one ring, but two rings with distance dr, elemental distance, so that we have here some differential thing, annulus. Can you imagine it? I hope yes. Well, how is the probability that the center of a randomly chosen fiber, sometimes for shortening I say that the fiber, I mean the center of fiber section in this moment, that the center of randomly chosen fiber lies inside the differential layer Ri plus dr in this differential annulus. Okay? How is the probability? Number of fibers in all protruding fibers which are here is dnh. All fibers which are in hyannis sphere, which are lying in hyannis sphere, are nh. So the probability that randomly chosen fiber from hyannis sphere is lying in our differential annulus must be dnh by nh. Okay? Is it well? Yeah? Let's imagine that inside of such elemental annulus is more smaller rectangle dx times dy. This elemental rectangle, okay? dx times dy. And let's formulate the probability that the center of fiber, which surely is lying inside of our differential annulus, is lying also in our elementally small rectangle dx dy. Yeah? Let's think only about the fibers which are lying inside of our differential annulus. It's sure in the moment. And then how is the probability that the one chosen fiber which is lying in our differential annulus is lying especially in our rectangle dx dy in our picture. It's easy. It is area of this rectangle dx dy by total area of differential annulus, 2 pi r dr. Sure? Yes. Well, then we can formulate the probability that the center, I must say it is a conditional probability, this second, isn't it? So-called conditional probability. The probability that the center of the randomly chosen fiber lies inside the infinitesimal rectangle, this small, is what? Is a probability that the random chosen fiber is lying in our elemental annulus times the probability that when it is lying in the differential annulus, it's lying also in our elemental rectangle. Therefore, this probability that the center of the randomly chosen fiber lies inside the infinitesimal rectangle dx dy is dnh by nh, this here, times this here, times this. Yeah? Such probability we will call dqxy. this repetition of our equation from last slide. Using known equation for DNH. NH we needn't to explain, it's possible to stay by symbol NH. But using the equation for NH, we obtain this here on the place of NH for dq. So we obtain, after rearranging this expression, dq xy is this here. But we also know from elemental geometry, from old Pythagorean theorem, that radius is square root of x square plus y square. Yeah? No? Pythagoras. Old Mr. Pythagoras. Well, so that we can write on the place of earlier r, it's here and here, we can write square root of xy plus y, x square plus y square, yeah? And so we obtain the probability that random chosen fiber from hyannis area is lying in our elemental rectangle dx dy. This probability dqxy is given by such expression. Yo? Well, I think time is running. In this moment, we break our lecture, and we will continue in the next lecture. We will finish this concept, this model concept, and then we will compare our results with experimental experiences. Yes, for this lecture, it's all. Thank you for your attention, and see you in the next lecture. Thank you.